Hi guys, in this video I am going to now find the capacitance for a cylindrical capacitor. Right? So what does a cylindrical capacitor look like? So there is one metallic cylinder of, let's say, radius R1, and then around the same axis, right, there is another cylinder, again metallic, of radius R2, right? And we need to find the capacitance for this combination. So let's get started. Same logic as we have done for other capacitors. So to recap, what is the basic equation? So we know that that's Q is equal to CV. So C is equal to Q upon V, right? C is equal to Q upon V. So which means if the capacitor has a charge Q, if you find the potential difference between the two plates, take the ratio, we get the capacitance, right? So the way we start off is, as always, we'll connect these two to batteries. So let's say there is one battery, one wire connected here, one wire connected to this, and now there is some charge here on the inner plate. Let us say there is a charge plus Q, and on the outer plate there is a charge minus Q. Okay. Now once we inject these charges, right, these charges will cause their potential to change. So this will have some potential, the outer one will have some other potential. So let's call this potential inside, let me call this a different color. So let's say this is my V plus, and this has potential V minus. Okay. Now we know the Q, the charge is given. So once we find the potential difference, right, we'll take the ratio and we'll get our capacitance value. So how do we do that? So how do we get the potential? As always, we will first find the electric field, right? We'll find the electric field, and then second we will say that we'll say that V is equal to minus integral E dot dr, right? From where to where? From the outer plate to the inner plate. Why? Because you want to find V plus minus V minus. So here my V, right, my potential difference is going to be equal to V plus minus V minus, right? So we'll go from, let us say, some point here, let us say from A to this point B, right? And in the process we'll find out what is the potential difference. So now let's get started. So let's first find the electric field, right? Where? Electric field? In the cavity between these two. Why? Because we need to take a charge from A to B and need to find out what is the, and we need to evaluate find this V. Now let's say I want to find the electric field at this point, some point here, right? This point is, let us say, at a distance R from here, right? How do you find that? Again, so we'll just use, Gauss's theorem, Gauss's law. So we'll just say, I'll take a Gaussian surface and we'll take it as a cylinder, right? So let us say there is this distance, so roughly here. So let us say there is right? So this is my Gaussian surface. Right? Now for this, so I've taken a cylinder which is kind of smaller in radius than this R2, but more higher radius than R1, right? And this has got some height, or some let's call it height. And this height is, let us say, this is my X. This height is X. Okay. Now we need to find the electric field here. So we'll just apply Gauss's law to this Gaussian surface. So we'll say integral E dot ds, right, is equal to Q inside upon epsilon naught, right? Q inside what? Q inside the Gaussian surface, right? Now, one assumption I'm going to make is that the cylinder is very long. Though I've shown that, the cylinder, the diameter and the height, they kind of look the same. But assume that the cylinder is much longer. This length L is much greater than R1, R2, and so on, right? So assumption I'm going to make is L is much greater than R1, R2, etc. Right? So effectively it's like an infinite cylinder. Effectively, right? So at any point, what will be the direction of electric field? Electric field would be always outside. It will not be up or down. It will always be radially outwards. So if I take this point, my electric field vector, right? Electric field vector will have this direction. This will be my electric field vector, right? And now I can evaluate this. If I take any point here, any area element, any ds element, what will be the direction of ds element? That also will be radially outward, right? So which means E and ds, they have the same direction. So now this element E dot ds, right, would be equal to E into ds into cos of angle between them, which is 0, right? Because they are both pointing radially outward. At any point they would be radially outward. So this would be E dot ds into cos of 0, which is nothing but equal to E into ds, right? And what is my Q inside? So now the charge plus Q is uniformly distributed. It is distributed over length L. But here I'm looking at the section. I'm looking at a section. Let's say I'm chopping the cylinder into a section which is of height x. So what will be the charge inside this? So it will be, charge is going to be Q inside would be Q total, Q divided by this whole length divided by L into just this length, into x. So once again, total charge divided by length. So charge per unit length into this length x. This is going to be my Q inside, and rest is pretty straightforward. So it will be integral over closed surface E dot ds, which is nothing but now E ds. So E ds is equal to Q inside, which is Q into x by L, right, divided by epsilon naught. Now here E is going to be, again, by symmetry at any point on this cylindrical surface of the Gaussian surface, E is going to be same, is going to be constant, right? By the way, it's kind of, I didn't mention this very specifically, but just wanted to remind that we also, when we do this E dot ds, we also have to look at the E dot ds for the upper lid and the lower lid, But what happens here, if I take any point on the upper lid, any area element here, area element is in upward direction, or here it's in downward direction, but my electric field would be outward. So the angle between them is 0. So there E dot ds would become 0, right? So therefore I'm evaluating this only for this surface. And in fact, to be more precise, I should not say E dot ds over this. I should just say E dot ds now over not over the closed surface, but over the cylinder. So this is just E dot ds over the cylindrical surface. I'll say over the cylinder. The cylindrical surface, right? Cylinder. So now my E is constant, so I'll take this E outside as the coefficient. This will be E, and now I have integral ds over the cylinder. What will that be? That'll be 2 pi. This radius is r, right? So 2 pi small r into x. I'm talking about the surface, the cylindrical surface area, right? Into integral ds over the cylinder, right? That would be equal to Q into x by L upon epsilon naught, and this would be nothing but E into 2 pi r into x, right? And this is equal to qx upon L epsilon naught, right? Now x and x will cancel, and then we now continuing here, right? Now what do we get? So now we get E is equal to, right? E is equal to Q upon 2 pi r, right, epsilon naught, right, into L. Okay. So this is going to be my my electric field. If I just move this here, so I can say E is equal to Q upon 2 pi epsilon naught r into L. Okay. Now, so far so good. So I found my electric field now, and its direction is radially outward. So now next step is I want to find the V, right? So next step is I want to find the potential difference V, and what is V going to be? Same expressions. This would be minus integral E dot dr, right, from A to B, from this point A to this point B, A to B, right? This is my A, this is my, let's say, point B, okay? So from A to B, right? And that would be, what is my E dot dr? Let's first evaluate this element. So E is outward, and R, my radius vector R, this is my radius vector R, right? R, this is also radially outward, right? And also my dr would be what? Dr would be small change in R, so I'll take this as my dr. So this is my dr vector, right? R and increase in R, this is dr. So now we'll say that E dot dr vector, right? This is nothing but equal to E into dr into cos of 0. Okay, cos of 0, so which means this is 1. So this is equal to E into dr, and now we have V equals minus, right? Minus integral E dr, right? E dr from A to B, and now we'll put the value, we'll get the value of E from here, right? So this would be V equals minus integral Q upon 2 pi, Q upon 2 pi, right? Epsilon naught L into R, right? Into dr, right? From A to B. And now Q is constant, 2 pi epsilon naught L, all these are constants. This would be nothing but 1. So this would be, so now we have my V is going to be equal to minus Q upon 2 pi epsilon naught L, right? 2 pi epsilon naught L into integral 1 upon R dr, and now R will go from A to B, and what is, now we'll put the value of R. So when it's at A, what is the value of R? R is going to be R2, right? And then inside cylinder it's R1. This would be from R2 to R1, right? And so V is equal to minus Q, and what is the integral of 1 upon R? This is nothing but log R, right? So it would be Q upon 2 pi epsilon naught L into, this would be log R, right? From R2 to R1, right? There's a minus sign here. If you take the minus sign inside, I can flip the signs, right? So I can write this as, so this is equal to, or let me just, do this. So this minus Q upon 2 pi epsilon naught L, and this would be log, right? Log R1 minus log R2, right? Now what is log A minus log B? It is log A by B, right? And if I take the minus sign into account, this will become, if I take the minus here, it will become log R2, it will become log R2 minus R1 if I take the minus in, right? So it will be, and what is log R2 minus R1? It will be log R2 by R1. So now my V is going to be equal to Q upon 2 pi epsilon naught L into log, right? R2 upon R1. Why is that? This is nothing but log R2 minus log R1. And here this minus when you take inside, that's what we get. Finally, we got the V. Now what do you want? We want Q upon V. That's my C. So now C is equal to Q upon V, and that is what? So if you take Q upon V, so this 2 pi epsilon naught L will go to the numerator here. So this would be 2 pi epsilon naught L, right? Upon log R2 upon R1, right? So this is going to be my capacitance, right? For a cylindrical capacitor. Thank you.